All right, so this is Physics 1C for, what's today, the April the 9th. Today what we're going to be talking about is we're going to be doing this problem that's right here. If you want to go ahead and start working on it while I'm talking, you can. We're going to talk about that, and then we're going to discuss the magnetic field of a circular loop, parallel conductors, and if we have time, we're also going to talk about Ampere's law. Okay, does anyone have any questions about anything before we get started? I'll do a brief review of what we did at the end of class last time as well. Okay, so what we did last time at the very end of class was we found that if you have a wire, and we can say that it's like a very long wire, then when you're some distance away from the wire, like let's say that this distance right here, we call it R, then at this location right here, if there's current flowing in the wire, so let's say that there's current flowing in the wire like this, we say that that current is going to produce a magnetic field at that location, and the magnetic field is going to point into the page, and the size of the magnetic field at that point ends up being equal to a constant that's called mu naught multiplied by the size of the current divided by 2 pi multiplied by r. On the top, the magnetic field points in, so the field up here is like this. Oh, sorry, wait. Am I getting this right? I'm saying in, but I actually mean out. These mean out, and on the bottom, the magnetic field points into the page, like that. And that's the expression that we need. The only expression we really need to solve this problem that we're going to look at here. So a wire carrying current produces a magnetic field, and this is the value, assuming that you make the wire very long and the distance r relatively short relative to that. So we want to use this idea to solve this problem, which is number 15 from a different textbook. It says that there are 3 long parallel conductors. Before I do this, I should at least ask, do you guys have any questions about what I just said? Why the field points in the direction that it does, or any questions at all? All right, so let's see how we can solve this problem right here. So it says 3 parallel conductors each carry a current I equal to 2 amps. Here's the figure. So each of these currents is coming out of the page. That's what these dots represent right here. So you're supposed to imagine that there's a very long wire extending into the page and out of the page. And you've got some distances here. And you know that, so this is an in view of the conductors with each current coming out of the page. We're taking A equal to 1 centimeter. We want to determine the magnitude and direction of the magnetic field at each of these points, A, B, and C. Okay? So let's go about doing that. Let's make this just a little bigger here. Okay, so you guys tell me, if I think about these as, I'm going to label these as like 1, 2, 3, just so we can have a way to label what magnetic field we're actually calculating. So due to current 1, can you guys tell me, well, maybe I should show you for this one, and I'll let you guys figure out the other two, okay? So when you have this current coming out of the page, right, it effectively creates a magnetic field that's pretty much circular in nature. So the way I think about this is, if this is the radius that we're going to be using, that's going to be our radius r for that equation right there, then the way I think about it is there's effectively a circle. Which way does it go? It goes this way. It goes in this direction, okay? And that circle is the direction of the magnetic field. Like that. The field points like that, and like that. That's the direction of the magnetic field. Let me try to do that again, but just do it with a thinner pen. Or I could just zoom out a little bit, I think. So there's a magnetic field here, and it's circular in nature, so it basically points along a circle, which means it also needs to go through that point, and then around like this. That's kind of a little bit better. So that's the direction of the magnetic field. It's circular in nature. So at this point right here, the direction of the field, I would say, is basically like that. That's your magnetic field. Does that make sense to you guys? It's a circle that goes around that object. The other one, I'm going to draw one right on top of this. It's going to look bad for a second, but I'll try to fix it up. The other one, like I3, for example, so that's for I1. In fact, we could call it B1 if we want to. For I3, we'll use black. So this one, coming out the way that it does, you point your thumb along the direction the current is flowing, and then you draw a circle. So now it's going to have a circle that goes like this. That's the direction of the magnetic field for 3. Okay, which means at this location, right, the magnetic field vector is pointing like that. Can you guys follow that? We're going to take off all these circles here in a second, but I think it's worthwhile. What? What's up? Question? Yeah, that's where magnetism comes from. It comes from these wires. Yep. So then this wire right here, you can imagine for yourself that it's going to also produce a circular magnetic field. And maybe you guys could tell me at this location, maybe you can envision it in your head right here. What direction is the magnetic field going to point here? At that orange dot right there, point A, due to current 2. What direction is it going to be? It's either going to be up or down. What's it going to be? It's down, right? And again, this is like you say, there's a circle. It's a bigger circle now, right? It's going to go all the way around here. I know that's horrible. Sorry about that, but... And then you draw a line tangent to the circle here, and that's B2. Now let's get rid of the circles. What's up?
It's a weaker magnetic field, right?
Yeah, because you're farther away, so it's going to be weaker by a factor of 3, I think, right? That's right. So there's your fields. Look at the way they look now. We're going to redraw them without all the circles, okay? I think I should be able to just erase the stuff that I was writing, right? Okay. So let's get rid of the circles. But you still should be thinking circles, right? That's the reason I'm drawing those, is you need to be thinking about circles. If we had a compass or something like that, you'd use a compass to do this. Okay, I erased those, but we'll write them again. Okay, so let's draw in. Maybe go down to a smaller ink. So this one we said we're going to call this one 1, we're going to call this one 2, and we're going to call this one 3. And we just found that if you go to this point right here, that the field created by 1 basically points along a line like that. That would be what we call B1. And then the field for 3 we said is going to point along a line like this. It's going to be B3. They're going to be equal to each other. And then the field for this one is going to point down like this, although it's going to be, straight down. Ooh, sorry. Writing down hard. There we go. Those are the 3 vectors that we have. And what are they equal to? Well, B1 is equal to mu naught times I divided by 2 pi a, because that's the distance. A is the, no, not a. Sorry, it's going to be a times the square root of 2, isn't it? Because if you have a square, ooh, man, it's getting on the edge. Let's go over here. If I have a square and it has a side A and a side A, or in this case A and A here, and I want to know what that distance is, the length of this side is always going to be a square root 2. You use the Pythagorean theorem to point that out, or to figure that out. All right. There's not a lot of room here. I need to move this over here. I don't really need this. We'll just move it up here somewhere. Okay, so that's a B1. And then what's B2? Okay, B2 is going to be equal to also mu naught times I. And then we have to divide by 2 pi. And now I would say we're multiplying by the distance from I2 to here, which is, I think you guys can see, is 3 times A. 3A. And then B3 is going to be exactly the same as B1. Now these are vectors, right? So we need to add them using vectors, meaning that we need to basically break each one of them up into components. However, in this case, since B1 and B3 are equal to each other, I would say that the components, for example, that point like this and like this are going to cancel each other out. And that is just way too thick to be drawing on that picture, at least. So the components of this vector, B3 for example, are going to point this way and then that way, right? One this way and like that. This one's going to be, the angle here is going to be 45 degrees. And that means that this side, for example, over here would be B3 times the sine of 45. But this one, what I'm saying, is going to cancel out with the x component for B1. So really what we're going to get in here is that the total magnetic field at that location is going to be equal to something like B1 times the sine of 45 plus B3 sine 45 plus B2. And all of these are pointing in the negative j hat direction if we define up to be positive y and then right to be positive x. Does that make sense to everyone? Does anyone have any questions? No? Okay. So, the answer then, something like B1, B2, and B3, they all share in common this mu naught I divided by 2 pi thing. And the first term then would have 1 over a root 2 multiplied by sine 45, but I think sine 45 is the square root of 2 over 2, right? So then plus B3 term has 1 over a root 2, and then that's multiplied by root 2 over 2. Oops. And then plus, and just to be clear here, because I don't want to be too, sine 45 I'm replacing with the square root of 2 divided by 2. And then the last term was just B2, and B2 had a 1 over 3a in it, right? And I guess since we're putting the j hat on here, we should really be identifying this as a vector. So what do we have? The root 2's cancel, the root 2's cancel, so it's basically something like that. 1 plus a third, which is 4 over 3. So I think this is going to be equal to something like oh, and this is negative j. Negative j. This would be equal to the magnetic field at point A. Is that right? We'll calculate what it is too. Did I do that right? You guys have any problem with that math? Does anyone have any questions? Did you guys follow all of that? Is that kind of confusing? I should also identify what mu naught is, in case anyone's confused. So the symbol mu naught here, so mu naught is equal to 4 pi times 10 to the negative 7 Tesla meter over amp. All right. So we'll be doing 2 times 4 pi. Wait, I think this one you have to actually put the times in front of it. Times pi. And then times 10 to the negative 7. Times 2. Oh, I already put the 2 in there. Times the current I. The current I was 2 amps here. So times 2. and then divided by 3, divided by pi again, and then divided by A, which was 1 centimeter, which is 0.01 meters. So we end up getting that 5.3 times 10 to the negative 5. So we get the magnetic field at point A is equal to that's the answer. You could also write this in a kind of cleaner way as 53 microtesla. It's a little easier to read, right, than the scientific notation. But you gotta know what micro means. All right. Does that make sense? Does anyone have any questions? Yes. Right, so that's based on the right-hand rule, right? So what you do is, how can I describe this without, like, so when you have a current that's coming out of the board, okay, I'm going to draw what it looks like. A current coming out of the board is going to create a counterclockwise current, okay? Got that? And a current that's going into the board is going to create a current that goes the other way, okay? That's the rule, basically, okay? So you can either memorize this, or you can use the right-hand rule. And the way you do that is this. So I want you to take whatever screen you're looking at, whether it's your phone or your whatever, and just take your thumb, or like the thumb of your hand, right? Okay, and then just like make a fist, and with your thumb sticking out, right? And then just put that right on top of where that dot is on your screen. Does that make sense? Just put the palm of your hand or the bottom of the fist of your hand so that your thumb is just coming straight out of the screen. And then the direction that your fingers rotate of your right hand is the direction that the magnetic field is going to be. Does that make sense? Okay. And then you do the opposite. You point your thumb into the screen for the one that points into the screen. Does that make sense? So that's how. Yep. Okay, any other questions? All right, so what I want you guys to do now is I want you to try to do this on your own. But I want you to do, first of all, I want you to do part B. So I want to find, part B, which is point B, and then I want you to do point C. Point C is going to be pretty similar to the one we just did. Point B should actually be easier because there's not going to be any trig. Okay? So give it a shot. I want you to try this problem, and you're going to find the magnitude of the magnetic fields, the magnitude of the magnetic field at point B, and the magnitude of the magnetic field at point C. Okay? And I'll give you like 5 to 10 minutes, however long it happens to take. I don't know how long it's going to take you. Just to make sure you guys kind of understand this, and then we'll follow up and see. Okay? I'll zoom out just a little bit here. Oh, I can maximize now, right? Just make sure you can actually read the problem. Maybe zoom it just a little bit more so you can see all the things. Once you're finished with that, if you want to try this one, you can. This is a really simple one. Okay, we'll talk about that one too. All right, so you got like 5, 10 minutes, and I'll check back. If you do have questions, feel free to ask. Kids doing okay? Was that enough time? Did you guys figure out B sub B yet? The magnetic field at point B? Mm-hmm. Anyone? Here, let's copied it together. Okay. Copy, paste. Oh, copy, click here, paste. There we go. Okay, so point B. What do you guys figure out about point B? What's going on with that one? Or B, it was like B1 and B3, I think. I know what you mean. These two, right? Yeah, because the one on top is going to send a magnetic field that's going to go this way, and the one on bottom, so that's like B1, right? I think, yeah. And then B2 is, or B3 is going to go this way. So those two just cancel, basically, right? And they're the same distance. So it's really only this one. And what way does the magnetic field for what we called current 2 point at this location? Yeah, there you go. So there is your magnetic field due to 2. And we can say that B2 would be equal to just pretty simply mu naught I divided by 2 pi. And then you multiply by or divided by the distance between point B and here, which is 2a. That one's pretty easy, right? And it's also going to be times negative j hat. I mean, you can calculate this if you want to, but... okay, so then point C. Did anyone have any questions about that part? Did you guys get the other one yet? Have you had enough time to get point C? Do you need more time? Let's at least talk about the directions. So the magnetic field due to I1 is going to point tangent to a circle. The circle is going to have this radius from this point to this point. So you basically go out to that point and think, okay, well, if I draw a line from the center of a circle and I want to draw a line that's tangent to it, right, then it's got to point, oops, it has to basically be perpendicular to the radius vector, right? So that would be what we call B1. And I could probably erase this piece. Right? That's B1, and then B3 is going to be similar, but it's going to be pointing this way. Those are going to be the same length vector, so that's B3. They don't look the same, I know, but... And you know what? We can make it at least close. Just make this a little bit longer. Okay, so there's B3. These are vectors. And then this one, B2, is going to point straight down. Okay, and then we break these into components, right? And we notice again that the x component of this vector and the x component of this vector are going to be equal and opposite, so they cancel. And again, we only have to end up worrying about the y components. And again, this angle is going to be 45 degrees. So this side over here on the right is going to be B1 sine 45. And over here it's going to be B3 sine 45. That's exactly the same thing. Okay. So then what we have is that everything ends up pointing in the y direction. So if we sum up the magnetic field at point C, it is going to be basically just b1 sine 45 plus b2, sorry, b3 sine 45, and then also we need to subtract b2 because it's down, right? Every term is going to have a mu naught I over 2 pi a in it. This one is going to have a 1 over a root 2. This is going to be very similar to what we did before. So you're also going to have a square root of 2 over 2, and there's technically going to be 2 of these terms. That's both this term and this term added together, merge into that term there. God, that looks just bad. I'm not going to do it like that. All of those together are that first term, and then minus b2, and b2 is going to have a 1 over a in it. Because that's the distance from, not 1 over a, I put the a out front. Well, we'll just erase the a, I won't put it in there twice. Okay, so we get that, and then we can just solve it. What is this going to be? So this is the 2's cancel, the root 2's cancels. Is it 0? Is that what you guys got, was 0? Yeah, BC is 0. I was thinking, like, looking at the drawing even, these 3 vectors look like they add to 0, kind of. I don't know if they do to you guys, but one this way, one this way, one this way. You can imagine a ring right here in the center, and someone's pulling this way, and someone else is pulling that way, and someone else is, like, everyone's pulling in opposite directions, but they all just perfectly cancel out, right? So we get that. Anyway, that's a nice little problem. You'll see some stuff like that on your, you would see stuff like this on the exam if we had an exam, but you'll see stuff like this on your homework, and, you know, I don't know. It's just a little vector problem. We had problems like this when we were talking about point charges, right? So with the point charges, we would just add the vectors of the electric field for the point charges, and now we have these kind of like point currents. They're not points; they're lines of current that come in and out of the board. But when you cut them, they kind of look like points. I don't know. If that makes any sense. Okay. Do you guys have any questions? Oh, I was in the wrong thing. Working on C. Is it 0? Am I tripping? Yep. That's funny. I was doing something wrong. And someone shared a little GIF. I like that. All right. So, can you eat in class? Of course you can eat in class. Why would you not be able to eat in class? You can do whatever you guys want. I don't care. Okay, so you want to talk about this one real quick, too? This one's really easy. Let's talk about this one. You want to try to do that one? You guys tell me real quick. You can answer in the chat. A, B, and C in order, like separate with commas. What's the direction of the current in A? What's the direction of the current in B? And what's the direction of the current in C? So for A, you'd put either left or right. For B, you'd put either in or out. And for C, you'd either put, I don't know, northeast or southwest. Or what do you guys think? Think about it. What's the direction of the current flowing in the wire in each of these cases? Shouldn't be too hard to do. So you say that it's, anyone else want to try to answer? Nothing wrong with getting it wrong. I encourage you guys to be wrong. Wait, is Cam? That's what I thought, yeah. Cam, you're actually in my 1A class, aren't you? I mean, you're more than welcome to hang out here. It's fine. Right, out, left. Yeah, everybody, you should try to guess, even if you don't know if it's right or wrong. It makes no difference if you're right or wrong. The whole point is to guess and then see, you know. Are some of you not able to type in the chat? I don't mean to be rude if that's the case. I'm not trying to. Okay, I guess that's all the answers we're gonna get. All right, so the one on the first one here, yeah, I think that someone said that it needs to point left. Is that what most people are saying? You guys are saying that the current here has to flow this way, and then the current for this one you guys are saying is out, so we would put a dot, right? You can imagine that if you point your thumb out of the page right here, the fingers of your right hand sweep around in a counterclockwise direction. This one, the side with the dots, if you look at it, if you're riding along the wire, the side with the dots is always on the left, right? So if I'm riding along with the wire to the northeast, then the side of the dots has to be on the left. The side with the x's is on the right. Or you can point your thumb in the direction of the current, and then your fingers sweep out the direction of the magnetic field, however you want to do it. Hopefully that makes sense to you guys. You have any questions? Okay, we'll do probably the next two problems, and that will be about all we can do. I don't know how long this one's going to take. So this is it's an example problem, but it's really more of a proof than anything else. So we have this segment of wire, okay? Calculate the magnetic field at point O for the current carrying wire segment shown in the figure. The wire consists of two straight portions and a circular arc of radius A, which subtends an angle theta, okay? So you've got your wire, and it carries current that flows like in here, and then through here, and then down to here, okay? And we want to find the magnetic field at point O due to this type of a figure. And we're gonna just draw on the figure here, because I can't possibly draw anything as nicely as they've already done here. Now, the theory of what we're going to be using to solve this comes from one of the things we talked about last time, which was the Biot-Savart law. And I believe that the Biot-Savart law says that if you take mu naught I divided by, I think it's 4 pi, and then you integrate something called ds cross r hat, where ds is a segment, not r, r hat, and then you divide by the distance between the point r squared, the distance from the dot to the distance from basically the wire to the dot, to the O. That's going to give you your magnetic field, right? So how to use this it tends to be kind of tricky, all right? But we're going to start off by looking at the segment A prime and A, okay? And I'm going to draw inside of here a little ds vector. That is a current element vector, you might say. And then I'm also going to draw a radius vector. It's going to clutter up the picture for a second, but the vector always points from where the current element is to the point that you're locating. Why does that feel wrong to me? No, that's right. That's right. Because if I had a point charge, right, Q, and I come out to some point P right here, and I wanted to find the radius vector would always go from the object to the point, right? That's where the position vector is drawn. Okay, I just had to think about that for a second to make sure I wasn't wrong about the way I was thinking about it. So, yeah. Now, we've got these two vectors, ds. Oops. These two vectors, and I'll just draw them over here to the side. The ds goes this way, right? And then the other vector points basically parallel to it out to the point O. That's your r vector. Which means dr or r hat, is going to be a vector that points like that. So with this situation, this is for the segment A prime A, right, between here and here. What would r hat cross ds be equal to? How do I find the cross product between two objects? It's 0, right? That's exactly right, because it would be the magnitude of this times the magnitude of ds, which we'll call ds, and then times the sine of the angle between the two of them, which in this case is 0 degrees. So what that means is, now let's erase some things here now that we can just go back to talking about this. what this means is that this segment right here doesn't produce any magnetic field. We don't even need to worry about it, right? Likewise, the same thing would be true down here for CC prime, okay? Because your R vector is going to be parallel to the current, okay? So there's not going to be any magnetic field produced at point O for these wires right here. That doesn't mean they don't produce magnetic fields, because the one on top right here produces a little magnetic field in this direction, okay? The one on bottom produces a little magnetic field so that it's like this, right? I think I did that right. Yeah. So there are magnetic fields. They're just produced in this region here and here. There's just none produced. There's no magnetic field produced at point O. Hopefully that makes sense to you guys. Okay? All right. So then that means we really only need to think about the magnetic field produced between points A and C, right? And already in the picture then, this ds vector has been drawn for us, and an example of an r hat vector from this particular location has also been drawn for us, right? Okay. So now we think, what is r hat cross ds? Or sorry, ds cross r hat in this case. So from AC, let's see what ds cross r hat is going to give us. Okay, first of all, what's the angle between r hat and ds in this picture? And in case you can't tell, and I'll draw my own version of it here, the position vector would be drawn from here over to O. God, that looks awful. How to do this? Man, my hand's like cramping up a little bit typing this thing. It's 90 degrees, thank you very much. You can see it, right? It's 90, it has to be 90, because R is a vector that basically points from the arc of the circle out to point O. It goes basically that way, that's where the direction R goes. And then ds is parallel to the wire, or tangent to the wire, you might say, whatever you want to call it. So that means the angle between the two of them is 90 degrees. That's right. Okay, so ds cross r hat then is going to be ds, I would say, times the sine of 90. And that's just ds. Pretty simple, right? But I'm also going to say that there's a relationship we know from radian measurements of circles that you can relate the arc length to the angle, right? You can relate the arc length to the angle, like that. You can also relate the arc length of a finite line element, ds, to rd theta then. So that's how we're actually going to do this. So let's put this all together. Our magnetic field at point O is going to be mu naught I over 4 pi, because that always shows up. The size of the current determines the field. The other things are constants. So there's that, and now we're going to be integrating, basically just, instead of just ds, although we can do this in 2 steps, I don't know. So it would be just ds over r squared, but what we're going to do is we're just going to replace the ds with rd theta, okay? And what's r in this case? What is r equal to? It's just equal to a, right? So our equation now is basically going to become a d theta divided by a squared. There's something else I left out of this, which is that ds cross r hat actually points in a specific direction. What direction does it point in? So use your right hand rule, point your fingers from ds, which is this way, right? And then r hat, which is this way. So take the fingers of your hand and rotate the fingers of your right hand, point them along ds, and then rotate them to here and tell me what direction your thumb points into the screen. So that would be like what, negative, let's say k hat maybe? Let's call it negative k hat. That's like in, right? Okay, and when I say that, I mean like this is x and this is y. Then z comes out of the board, right? So the negative k hat would be into the board. Okay, so good. So this is times negative k hat. And now we just need some limits, okay? Now we know that it subtends an angle theta right here, right? So what I'm going to do is I'm just going to make my limits go from 0 up to the angle theta like that, okay? So we'll go from 0 to theta. And of course, that's a really easy integral to do, isn't it? Because it's just the integral. A is not a function, right? So you just end up getting mu naught times I divided by 4 pi a multiplied by theta, and then it points in the negative k hat direction. That's it. That's the answer. That's pretty easy. I don't know if it's easy. I think using this equation is pretty hard all the time, but this is a pretty simple thing. Do you guys have any questions before we go beyond what this says? So what if it's a circle? Like, what if you have a loop? Why did I push B there? No. I have a loop of current, I, and I go to the center of the circle right here, and I want to say, what's the magnetic field right here at the center equal to, right? So, what would it be? We found what it would be for a portion of the circle, right? Where the angle made here was theta. What would it be for the whole thing? What would theta be equal to? 2 pi, yep. So for this guy, you plug in theta equal to 2 pi, and what do you get? You get mu naught times I divided by 2a. You're going to say it in degrees. That's okay. If you said 360 degrees is fine. It's just that basically, like, when we did this locked us into using radians. Does that make sense? This is a radians only statement. No degrees. That is only true in radians. If you want to put it into degrees, you need to have a conversion factor right here. But regardless, that's the magnetic field of a loop, of a circular loop. Does it make sense? So here's a problem we can do with this one. All right. A conductor consists of a circular loop of radius r equal to 15 centimeters and 2 long straight sections as shown in the figure. The wire lies in the plane of the paper and it carries a current I equal to 1 amp. Find the magnetic field at the center of the loop. Okay? So what I'm going to do is say that this problem consists of basically a combination of two things. You've got a line that has a current I, and you have a loop that's basically right on top of it. They're connected, of course, so they have the exact same. And the loop basically has also a current I. And the direction of it, if you can tell from the picture, is like this. They're both the same. And our goal is to find the magnitude of the magnetic field here. And what I'm going to say, it's basically going to be that the magnetic field at that location is going to point into the page for both of them. And the total field is just going to be the field due to the line plus the fields due to the ring or the loop. So that's going to be, if we call this distance r, we said the magnitude of the magnetic field for a line of current is mu naught I over 2 pi times the radius, which in this case is r. Plus, for a ring, that's this one, mu naught I over 2a. Or, well, 2r in this case. A is the r, right? Let's write that. That's it, right? So we end up getting mu naught I over 2r times 1 over pi plus 1. Yeah, that's kind of bad. 1 over pi plus 1. Maybe we can calculate what it is too. We've got some numbers here, right? So let's do that. Oop, didn't mean to do that. So if I go here, it's mu naught. So mu naught, again, is 4 times pi times 1 times 10 to the negative 7. That's what mu naught is. Times the current. I think the current here was 1 amp. Oh no, it was locked to the screen. That's too bad. The current was 1 amp, so we just do times 1. And then, let's see, divided by 2, divided by 15 centimeters, that's 0.15. And then we just need to multiply by 1 over pi plus 1. And that's our answer, 5.5 times 10 to the negative 6. So I'm going to write that as 5.5 microtesla. Also times negative k hat, I guess, would be the right way to do this. Because it's also going to point into the board. Does that all make sense to everyone? It's a pretty easy problem, but it's just one that, you know, we can show kind of what's going on here. There's something else about this that's worth mentioning, which is now that we know that you can produce a magnetic field at the center of a loop by this kind of thing right here, there's a way that you could make the magnetic field even bigger, and all you would have to do would be to say, well, I know that for one loop of wire, I get a magnetic field that's equal to this. So if one loop of wire gives me that, well then if I take that same wire and I just keep looping wire around in a circle, right? Just take a big bundle of copper wire, right? And just bundle it up like this, just like loop it up in a circle like this. And then you run current through it. Then if you count the number of turns of wire that you've used, each loop that you add increases your magnetic field, right? The more loops of wire you can possibly get, the more coils that you can pack in will increase the size of your fields. Does that make sense to you guys? So N in this case then represents the number of loops. The number of loops determines how strong the field is. The more loops, the bigger the field. You have 2 loops, you get a certain field. You put 100 loops in there, you get 50 times as much field, right? Does that make sense to you guys? That's how you produce really strong magnetism. You've got loops and loops of wire, and I can kind of draw this back to something that we talked about last time, which, and I don't even need to show you the picture from here, I can just show you a picture from the internet. So if we look at the Atlas detector at CMS, or sorry, at CERN, let's see if there's a good big picture of it somewhere. What's the best picture here? Maybe this one. I don't know if you can really tell. This is when it was being installed. Maybe the picture from your book is fine. This one you can kind of see it. Not exactly though, because we're seeing the outer piece of it. This thing has a gigantic magnet in it though. And let's look at the picture from your book, because that really kind of should. It's this one, right? So if we go here, that picture right there, you can tell it's kind of similar to what we were looking at, but it's just a little bit. Oops, didn't you see that? There we go. This like ring right here is quite literally what I just described, just on a much more massive scale. It is a series of loops of metal or wire or something that all have, you know, current running through them and produce a gigantic magnetic field. And what this gigantic magnetic field can do, so I'm going to show you some of the stuff that that we kind of data you get out of a machine like this. So let's see if we can get a good picture of one of these things. Let's do this. That'll work. This is kind of a good picture of what I want to show you. This one's even better. This one's pretty good too. So, oh, that didn't work. It didn't pull it up. Which one did I like the best? I like this one pretty well. So, this is the kind of data that comes out of these machines. All right? It looks like a bunch of junk, but it is actual data. That's kind of indicated by this timestamp that's down here in the bottom right. And what's represented right here is every single one of these lines, okay? It represents a charged particle, okay? And in particular, I want to look at the lines that are like basically in this region right here. Notice that one of these particle curves to the left, and one of them, well, however you want to think about it, if it's moving this way, I guess you'd say it curves left, and the other one curves to the right. The thicker the wire, the better. It depends on how much current you can get to flow through it, because the thicker the wire, the thicker wire actually is better, for sure. Because then it would have less resistance. You can get more current through it. So I want to ask you guys this question. Suppose that you saw a particle and it moves this way, and you saw a particle and it moves this way, inside of what you know is to be a magnetic field. There's a magnetic field in this picture that's pointing into the screen, okay? What does that tell you about these two different particles? What's different about them? Why does one turn left and why does one turn right? Any ideas? What's making them turn? What's making them curve instead of move in a straight line? I probably didn't set this up well enough for you guys, did I? You're probably just confused at what you're looking at. Is that true? Oh, people started talking. It is, yes. It is like the copper wire and the magnet we saw in the video, exactly. That copper wire felt a force from the magnet, right? And these particles that are produced here are leaving tracks. And the direction they travel is because they're in a field, a magnetic field, and they feel a force. Some of them feel a force that makes them curve left, and the others make them go right because some of them are positive and some of them are negative. Does that make sense? In fact, the curvature of the track itself tells you something about how charged they are, and also tells you something about their mass. But the direction that they curve is purely either positive or negative. So one of these particles here is positive, and one of these particles is negative, basically. Does that make sense? Anyway. All right, so that's what these gigantic magnets can do, is they produce these magnetic fields that you can then use to gain information about particles that are produced in a decay event like the one we just see right here. And what's happening here is that there's a Higgs boson that's produced somewhere inside of here that's decaying down into two bottom quarks and depositing all of this energy in this region right here. And these are all these bars are basically measurements of energy that gets deposited into the detector that's gathered in various ways. We need that big of a machine for something small. Yeah, you do, actually. It's a really interesting way to say it. The bigger the size of the machine, the bigger the magnetic field you can produce. But the actual machine itself that powers all of this is called the LHC, the Large Hadron Collider, and it is huge. 27 kilometers around. That's Geneva. Okay. What's a better picture of this? I don't know. That might be one of the better pictures of it. Like, that's how big it is. The one I worked on was not this big. Oh, why can't it just give me the picture? What if I do that? Will it work? That's kind of good. I mean, what you're seeing in this image is like from space. Not from space, but like high up in the air, right? So you can see that there's towns here. Like, that's the town of Geneva. It also, this crosses between two countries. Part of the collider is in Switzerland, in Geneva. The other part of the collider, this region over here, I believe, is in France. I think it's France. And it's kind of a European collaboration. It's not just Europeans, because Americans work at this place too. But it's a collaboration of scientists all trying to find little tiny things. And they need to have the track that it moves along be 27 kilometers around, which is just insane. And they want to build a bigger one, because the size of the size of the track itself is what determines how fast you can get the particles moving. And what this collider does is you get particles moving really fast, and then you put them into this machine, and the particles are protons. You send one set of protons one direction, you send the other set of protons the other direction, you get them up to the speed of light, actually really close to the speed of light, something like 99.9995% the speed of light, as close to the speed of light as you really can get. And then you just force them to hit each other. You just take these two bunches of protons, which is quite literally just a bunch of hydrogen ions, right? And you just force them to hit each other. Have they found anything new besides Higgs? No. They found some things, but nothing interesting. Nothing like super interesting. Yeah, big oof. This whole thing was designed to find the Higgs. And it did it, but we were hoping that it would find something else. And if you know what the Higgs boson is, it was a particle that was discovered in 2012, was predicted to exist in the 1960s. It was the final piece in our puzzle of the periodic table of the universe, you might say, the Standard Model. And it's a particle that, through interactions with a field, produces mass. You can say that effectively. The reason why objects have mass is because of the Higgs field. Okay, the reason why an electron is not zero mass is because of the Higgs field, or because of the Higgs boson, you might say. And they produced it here. They're continuing to produce them. What does it say? Big dumb question. But if that giant magnet is there, how come it doesn't mess with the city? Well, it probably does, honestly. And I think what you're seeing here is that this is like cornfields or like pastoral like farm area, probably. I don't know. Definitely that magnet would 100% affect things that were near it. Like if you were trying to use a computer in that room, you got close enough to the magnet, you'd feel effects of it and stuff like that. So it would mess with things. Corn becomes GMO in a magnetic field. I don't think that's true. That's funny though. I know you're just joking. Anyway, so that's the LHC. It's used to probe the universe. We recreate the events of the Big Bang in a collider and produce particles that only exist for fractions of a second, and then we try to measure things about them. We try to measure their masses, their charges. You know, we do what physicists always do. We just keep measuring stuff, right? This is crazy, like in a cool way. I think it's fascinating. I mean, it's what I worked on for my PhD and stuff like that. The one I worked on, though, was not this one. It was called the Tevatron. It's in Chicago, or near Chicago. And this one's nowhere near as big. But yeah, I worked here for a while. This is called the Tevatron. And it's at Fermilab. Oh, this is a nice picture. So this one's a little simpler. It's only 1 kilometer in radius. So what does it make it? About 3 kilometers around, right? And there's 2 detectors. I worked on D0. Whoops. I worked on the D0 detector. The other detector is called CDF. CDF stands for Central Detector at Fermilab. D0 quite literally stands for a labeling system for the points around the ring. So there's like D0, D1, D2, D3, and it goes around. It's like A1, A2, and D0 is just the name. They decided to just use that. But much smaller, so we couldn't produce nearly as much energy. The difference is that this one has an energy of 2 tera electron volts, so 2 TeV, and the other one has a center of mass energy of 14 tera electron volts. So it's 7 times more powerful, basically. The other one that we just saw. 7 times more powerful, and you might notice, did I leave it up? 27 kilometers around, right? And the other one was about 3 kilometers around. So you can see where that ratio is coming from, right? It's not exact, but it's pretty close. This is 27 kilometers. The other one's about 3.1 kilometers. Then you take 3 times 7, you get 21. Okay, so it's about... Your question is, are there more theoretical particles they are trying to find specifically, or just smashing particles to see what comes out? Well, this is how we started. We just started smashing them together because we didn't know what else to do. Well, that's not true. We knew it was going to happen to some extent. But yeah, at this point, we are just continuing to smash particles together at as high of an energy as we possibly can, with the goal of just seeing what comes out. And currently, there are a lot of interesting particles they could find. In particular, we're looking for a whole kind of set of new particles that meet some type of what was the word for it? Some type of requirements. And one of the ones we're looking for that would be really exciting are what are called supersymmetric particles. The symmetry particles, yes, that's right. Supersymmetric particles. And what those are is, let me pull up a picture of the Standard Model real quick here so I can say more about what this is. So the Standard Model it looks kind of like the periodic table. This is it right here. It's full of some things you've actually heard of before. There's probably only one on here that I can guarantee you've all heard of before, and that's the electron. Okay, the electron is part of the Standard Model. Every particle on this list here, as far as we know, is a fundamental particle. Okay, there's nothing smaller than these things. We organize them into leptons and quarks. Yeah, quarks right there. There are 6 quarks, up, down, charm, strange, top, bottom. Sometimes these are called truth and beauty, but usually top and bottom. You'll notice there's 3 generations, okay? They get heavier as you go from left to right. Up and down quarks make up a proton, okay? The proton is made up of 2 up quarks and a down quark. The neutron is made up of 2 down quarks and an up quark. Okay? Almost all matter is made out of these 3 particles right here. All normal matter, stable normal matter, things like tables and books and people and dogs and cats, are made out of these things right here. Stars as well. Okay? Everything that we can visibly see in the universe is made out of just those 3 particles. Okay? At the collider that I just showed you, we're able to produce these heavier states, the charm quark, the strange quark, the top quark, and the bottom quark. These type of quarks would have existed in more abundance at the beginning of the universe when the universe was hotter, because when the universe is hotter, it has more energy, and more energy means you can have more massive particles. To give you an idea of the scale of their masses on these things, let's pull up one of these that actually puts their masses in there so you can see. Okay, so I've got a poster with something like this in my office. You can't really read that, though, can you? Maybe this one's just better? That one looks better. I really just want to look at the image, honestly. So look at the differences in these masses. So we measure mass in electron volts divided by c squared. These ones are in mega electron volts. The electron is extremely tiny, 0.511 mega electron volts. But look at the top quark. 173 giga electron volts. So that's 173,000 mega electron volts. This one is significantly heavier. This one was discovered at the place that I worked at Fermilab in 1995 when I was younger. I wasn't old enough at that time, but I remember reading on the news that they'd found the top quark. And it was done in America. In fact, I believe all of the particles here were found in America, and I think all the red particles, minus the photon, were found in Europe. Anyway, so that's the standard model, right? Okay, and your question was, are there more theoretical particles? We found all of these. You notice the photon's one of them too, right? We found every one of these particles on here. We've measured their masses to a lot of accuracy. Some things like the Z boson here have been measured to extreme accuracy. This number is not doing it justice. This is one of the most precisely known constants in the universe, is the mass of the Z boson, because we've been able to probe it with just tons and tons of data from these 2 colliders. Anyway, it doesn't really matter. This is just, we know this with a lot more precision than is actually shown here. So supersymmetry poses the idea that maybe for every single one of these particles, there is what's called the supersymmetric partner. And the supersymmetric partners are named by putting an S in front of the name of the particles. So like the up quark, the supersymmetric version of it is called the SUP, S-U-P, like SUP. The supersymmetric version of the down quark is S down, or S down. Charm is SHARM. This one would be S strange with 2 S's in front of it. This would be bottom, and this one would be stop. And then for the other guys over here, the electron is the selectron, this is the SMUON and the STAU, and then this is, selectron, neutrino, etc. So these guys, you put an eno at the end of their name. You get the gluino, the photino, the xeno, and the weno, and then the Higgsino, along with something called the neutralino. Now, what's the point of just naming a bunch of particles? Why would we want to do this? The reason why is because there are things in the universe that we don't understand right now. I don't know if you guys know this, but we only understand about 5% of the matter contents of the universe. 95% of the matter energy content of our universe is made up of 2 things, dark matter and dark energy. And while dark energy is something that can merely be described as a force that pushes the universe apart, dark matter is something that we believe is actually physically something that we could find. Okay, it's something that we should be able to produce in these detectors, because after all, the detectors that I was describing to you guys, they're kind of like make everything machines. They can literally make anything that has ever existed in the universe. Only fundamental parts of the universe, though. We can't collide 2 protons together and suddenly have a piano pop out, right? But we can collide those 2 things together and pop out anything that has ever existed in the history of the universe or could exist. Anyway. Anything that can happen will happen. Anything we could produce, we will produce. We just need more events, right? It's just like if you roll enough dice, you'll see every possible combination of the numbers that could possibly come up on the dice. So the existence of all of this extra matter that we don't know about, don't understand what it is, one possibility is that it's made up of supersymmetric particles, and we just haven't been able to detect them yet. And one of its properties would be that it has to be neutral, and it has to be stable, because it doesn't decay. So I mentioned that in this picture, the electron, the down quark, and the up quark contribute to all of the normal matter in the universe. The up, down, and electron do. The rest of these particles decay. In fact, if you're taking 1D right now, Have you guys gotten to special relativity yet? Maybe not. When in 1D, when you start talking about special relativity, I guarantee you'll start talking about muons, because muons decay, but their decay rate is like microseconds, and they manage to get to the Earth anyway. And I'll let you guys hear about that later on. But the point is that most of these things decay. Dark matter does not seem to decay. It just hangs around. It clumps up, and it forms the bedrock of all galaxies, the kind of foundation that galaxies are founded upon. Our galaxy, the Milky Way galaxy, we know it needs to have something. You just started special relativity. Oh, okay, cool. Did you talk about muons yet? Calculating the time dilation related to the lifetime of a muon in the lab frame versus the lifetime of a muon in its... It's usually one of the first things people do. Not yet? Okay, it's going to be pretty soon, but I guess you're going on spring breaks. Maybe you won't do it until after, but man, special relativity. I really want to teach 1D. It's so fun. Relativity is really neat. Okay, so what was I talking about? Oh, dark matter. So the idea behind dark matter and why we need it is that galaxies tend to be rotating faster than they should. The way I like to think about this is if you're on like a merry-go-round at a park, like just the kind that you push. If you get pushed too quickly, you're going to be flung off of the merry-go-round. Okay? And that's basically what's happening to the stars in our galaxy. The galaxy appears to be moving so fast that the stars should technically, according to all known physics, they should be flung off into space. That's what should happen. And it's just not happening. And the only way that we can perceive that might work is if there's more gravity there than we can actually measure, which means there needs to be more matter to produce that gravity, and dark matter is that thing. It is sometimes referred to as dark gravity. That's what Neil deGrasse Tyson calls it. He calls it dark gravity. He thinks dark matter is a bad name. The gravity is definitely there. That's something that Dr. Hacking told me one time. I asked him if he believed in dark matter, and he said, well, the gravity's there. And I'm like, that kind of convinces me. I don't know. There's gravity that we can't see where it's coming from, and so we label this thing dark matter. Now, if dark matter is a thing, it can't decay, which means it can't be any of the things you see on this picture, okay? It has to be something that's neutral, because neutral objects do not emit light, okay? That's not entirely true. Neutral objects can emit light, they would often be composed of some kind of charged particles. So whatever this thing is, whatever dark matter is, it can't be composed of charged particles. That's why it needs to be neutral. Now, this goes back to the first picture I showed you when I asked you, what is it that's making these particles curve, right? And I said that the reason why they're curving is because there's a magnetic field, and the positive particles go one way and the negative particles go the other way. So this is the deal. This is why it's so hard to understand dark matter. Neutral particles leave no trace in our detectors. We can't make them curve. They just escape from our detectors. And the only way that we know that they're there is by using conservation of energy. We can count up how much energy we have here, and if we know the energy that went into the system, right? Conservation of energy says, if I know the energy of the incoming protons in this system, and they collide with each other, then the outcoming energy, at the very least, has to be equal to that, right? So what dark matter looks like in a detector like this is missing energy. Missing energy, what they call missing transverse energy. It doesn't really matter. The point is that it's the energy you don't detect. That's what dark matter is. So can you imagine how hard it is to find something you can't detect? That's the problem we're having right now. We can't find this stuff. And theoretically, supersymmetry, the idea that every particle has a superpartner, is one answer to the question. But we still haven't found any evidence of supersymmetry, and it pisses off all the scientists that work on this stuff. It's really sad. Like, the particle physics community isn't not like a sad state, but it's just like finding a needle in yeah, that's right. It's like finding a needle in a haystack, except neither one is actually there, and you can't see it. It'd be an invisible needle or something like that. And then if you tried to touch it, your hand would pass right through it. So it's wild. Dark matter is fascinating. I spent most of my time in grad school working on trying to solve and understand what dark matter is. Is dark matter theorized to have a stake in the universe expansion, or is that some? So it does, in the sense that it works against the expansion of the universe. So dark matter causes galaxies and stars to clump. So it basically drives galaxy formation, and large-scale structure formation is how the cosmologists would say it. Dark energy is the force that's pushing on all of space, causing space itself to expand. So dark energy is what we say is what's causing the universe to expand, and dark matter is the primary force of gravity that is drawing the galaxies together. Without dark matter, we would have no galaxies. The universe would be uniform, stars would be far and spread apart, and yeah, we wouldn't have galaxies. We wouldn't have planets. We might have some planets. I don't know, but it's just dark matter is the force that, or the thing that. Dark energy is the expansion. You heard Tyson say that? Neil deGrasse Tyson said that? Yeah, dark energy is the expansion. Some people like to call it vacuum energy. It's something that I wanted to study, but the field that I went into, we don't really talk about dark energy much because it's more for the field of cosmology and astronomy, because that's where the effects of dark energy start to play out. Dark energy only has effects when the distances between objects become very great. So the idea is that between the stars within a galaxy or something like that, they don't feel much force from this dark energy. But between galaxies, like from one galaxy to the next, if they're far enough apart, then they'll feel this force. And in addition to that, the force from dark energy scales with the distance between them. So the farther they get apart, the bigger the force of the dark energy force becomes. It's not even a force. I shouldn't say that. It's something. We don't really know what it is, honestly. What is this? Neil deGrasse Tyson. Whatever, Skiff. Yeah, that's good. This is so interesting, Tom Neck says. I could talk to you guys about this for years. I would never get finished, so I'm not gonna keep going. But if you guys do have questions about any of this stuff, let me know. I'm gonna stop the recording now. It's well beyond what I wanted to